and welcome to Otten Math. In this edition of Otten Math, we're going to talk about the fundamental theorem of algebra. Very interesting and important topic for Algebra 2, to say the least, so let's get started. All right, let's talk about some basic definitions and terms, and also the fundamental theorem of algebra itself. The fundamental theorem of algebra is going to say that for any polynomial, and remember, polynomial means many terms, where the exponent is greater than 0, the number of solutions is equal to the value of the highest degree exponent of the term in the function. So we go back to our original polynomial that we've been dealing with, I believe. For the past couple of lessons, I have negative 9x cubed minus 2x squared plus 14x plus 5. I find the term that has the highest degree exponent, that's going to be 3. And that tells me that there are going to be 3 solutions to that polynomial. So if I were to set this equal to 0, I'm going to find 3 values of x that would make that polynomial true. All right, so the highest degree exponent is 3. The number of solutions then is going to be 3. So the requirement is that in the polynomial, the exponent has to be greater than 0. All right, moving on. Okay, so some caveats and things to know about the fundamental theorem of algebra, and that is a solution may be counted more than once if the zeros, the factors, are the same. So in this example, I have x cubed minus 5x squared minus 8x plus 48, and that factors to x plus 3 times x minus 4 squared. So I have, in reality, I just have 2 different values, negative 3 and plus 4. But with respect to the fundamental theorem of algebra, I have 3 solutions. One is negative 3, and then the other one is plus 4 twice. All right, so you can count the solutions, or the zeros, more than once if the factors are the same. Second caveat is that the solutions of 0 may be real or imaginary. So they don't have to be real values, they can be imaginary values. But there are a couple of things we need to know when we talk about imaginary values with respect to solutions or zeros for a polynomial. And those are with respect to the complex conjugates theorem and also the irrational conjugates theorem. So in conjunction with the fundamental theorem of algebra, you also need to know that in some cases you're going to come up with an imaginary root or 0 or an irrational root or 0. And in both cases, you need to know that if you have one complex 0 as one complex number as a 0, then you're also going to have another one. And that other one is going to be the conjugate of the original complex number. So as it turns out, the both complex numbers and irrational numbers will always travel in pairs as roots. So you always have some multiple of 2 for the roots if you have an irrational number or if you have a complex number. So if I have a root and I find it's 1 minus 3i, then I know that the other root, there needs to be at least one other root that's going to be a complex number. It's going to be the conjugate of the original value. It's going to be 1 plus 3i. All right, so complex conjugates theorem says that if a plus bi is an imaginary 0, then a minus bi, its conjugate, must also be a solution or a 0. And then the irrational conjugates theorem says that if a plus the square root of b is a 0 of a polynomial, then a polynomial function, then a minus the square root of b is also going to be a 0. So if I have 2 plus the square root of 3 as a solution, then 2 minus root 3 is going to be a solution for, or a 0 for that polynomial function. All right, moving on. Descartes' rule of signs. And we're going to combine Descartes' rule of signs with the fundamental theorem of algebra to create a table in which we can determine the possible combinations of zeros, both real and imaginary. So Descartes' rule of signs has 2 pieces to it. The first is with respect to positive numbers or positive zeros, and the second is with respect to negative zeros. So what Descartes' rule of signs says that the number of positive or negative real zeros is equal to the number of changes in the sign of the coefficients, or is less than that number by a factor of an even number. So what does that mean? Well, when we're talking about positive real zeros, what we do is we set up the polynomial as it is. And then we're going to count the change in sign. So a change in sign would be from plus to minus, or be from minus to plus. Right, once we have the count of the change in signs, let's say it's 7, then we know that the possible number of positive zeros is going to be equal to 7 or a factor less of 2, less than 7. So it'd be 7, 5, 3, or 1 real positive zeros. So let's go through, let's use this example. In this case, we know that because we have an exponent of 6, we know there are going to be 6 solutions, or 6 zeros. So we know 7 is not a possible number relative to the example I just gave, but I wanted to give you an example of what they meant by less than the number identified by a factor of an even number. So it would be 7 or less by a multiple of 2. So let's count the changes in signs. Okay, so first I have a plus x to the 6th. Then I have minus 2x to the 5th. That's change number 1. Then I have plus 3x to the 4th. That's change number 2. Then I have minus 10x to the 3rd. That's change number 3. Now I have a minus again, minus 8x, and minus 8. So I have 3 changes in signs. So I can have 3, or I can have 1 positive real root. Now the way that you find the negative real roots is to then change x to negative x, and then figure out how many changes in signs there are from there. Okay, so x, the prior polynomial that we used, x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8 changes to negative x to the 6th. So negative x to the 6th, I'm going to rewrite as x to the 6th. It's going to be a positive value because I know that any value to an exponent that's a multiple of 2 is going to be a positive result. All right, so negative 3 times negative 3, for example, is going to be positive 9. Then I have negative x to the 5th. That's going to be a negative value. Times negative 2 is going to be also a positive. So I have positive 2x to the 5th. Then again, I have negative x to the 4th. It's a multiple of 2. So this remains as a positive value. I can change this to 3 plus 3x to the 4th. Okay, now I have negative x to the 3rd. It's an odd number exponent. So I know that value, that negative value is going to stay the same. But then I multiply it by a negative number. So now I have plus 10x to the 3rd. Negative x squared gives me a positive x, but now I have a negative value multiplied by that x squared. So this is the same as negative x squared. And then I have negative 8 times negative x. That gives me a positive 8x. And then I have negative 8. So I have changes in sign from plus x, there's no change in sign, plus 2x to the 5th, no change in sign, plus 3x to the 4th, no change in sign, plus 10x to the 3rd, no change in sign. Then I have my first change in sign from these two terms, from one to the other. So that's change number 1. And then I have another change in sign, that's change number 2. And then finally I have my last change in sign, that's change number 3. So when we go back to Descartes' rule of signs, we can say that the number of negative real zeros is equal to the number of changes in the sign of coefficients when x is changed to negative x. So it's going to be 3, or is less by a factor of an even number, 3 or 1. So I can have 3 negative real roots or 1 negative real root. Now, what I need to do now is create a table to determine the possible combinations of positive, negative real zeros, and also imaginary zeros. So let's go to our table, and I filled it out for us. So we know, going back to the fundamental theorem of algebra, that we're going to have 6 solutions. We don't know what the solutions are going to look like. They could be real or imaginary, but we can figure out possible combinations. All right, so I know that I need to have a total of 6, according to the fundamental theorem of algebra, 6 solutions, either real or imaginary. I know I can have either 3 or 1 real solutions, and I can have 3 or 1 negative real solutions. So 3 or 1 positive real, 3 or 1 negative real. If I have 3 positive real and 3 negative real, then I have no imaginary, because I have 6 total solutions. If I have 3 positive real and 1 negative real, then I need to have 2 imaginary solutions to make up the difference to get to that 6. I can also have 1 real and 3 negative real. So 1 positive real, 3 negative real, that gives me 4. I still need 2 imaginary. Or I could have 1 positive real and 1 negative real, in which case I'd be left with 4 imaginary numbers to make up the difference to get to 6. All right, so we're using the fundamental theorem of algebra to determine how many solutions there are. And then we're going to use Descartes' rule of signs to determine how many positive real roots there are and how many negative real roots there are. And then we're going to use the complex conjugates theorem to figure out how many imaginary numbers are left to fill the gap in order to get to the total number of solutions, knowing that the complex conjugates theorem tells us that if we have one complex root, then we also have to have another complex numbers root that happens to be its conjugate. All right, so we're going to end here. I want you to come and join us for some problems. Let's get this all straightened out so you'll be good to go on the fundamental theorem of algebra.